All right. So hello and welcome everyone to this channel of Tutee Learning. So today is a lecture number 9 on vector algebra, and we're going to cover a very important portion for vector algebra that is going to be new, something that you haven't studied in your physics so far, right? So today, now as you have seen that in the previous lectures, we have been finishing with the basics of vectors, starting with vector addition, subtraction, and certain properties regarding that. And after that, we discussed about product of vectors or product of two vectors specifically. So we saw that product of two vectors can give a scalar result. Also, it can be done to give the vector result, right? So this is what we have all covered in our previous class. So in today's session, we're going to discuss about what about the product of three vectors. Now simultaneously, if we look at a product of three vectors, again, we're going to have both. Either it will give a scalar result, either it will give a vector result. So depending on which, I will classify them as scalar trivial product and vector trivial product. So today, we're going to learn about scalar trivial product. So let's start about discussing about scalar trivial product. I hope I'm audible, and everybody, welcome back. And if you're into this particular platform, please like, share and subscribe this particular videos, and subscribe to the channel, so that because through this channel I'm trying to help all the students or all the aspiring JEE aspirants for upcoming JEE Mains and Advanced preparation. So through this particular platform, we are trying to provide free and good quality contents over the YouTube, so that you can prepare for your upcoming JEE Mains and Advanced examination. And these lectures are specifically targeted for the upcoming JEE Mains 2026, that is the January attempt, right? So before the January attempt, we are definitely going to bring up crash courses and one-shot lectures. So don't worry, we have planned everything for you. Just subscribe to the channel and hit the bell icon, so that whenever we are live, you get a direct notification. So let's start. So let's start with definition or understanding about scalar trivial product. So if I talk about what is the definition or how do we define the scalar trivial product. So let us say that we have three vectors with us. So let us say we have three vectors which are A vector, B vector and C vectors are the three vectors. Then the scalar trivial product is defined as is defined as A vector cross B vector dot with C vector. So whenever we see this particular result, it is called as scalar triple product. So scalar triple product simply implies that it is A cross B dot with C vector. Hi Mahendra. Alright, so therefore, and in shorter notation, we define and we represent this particular notation by a box of A vector, B vector and C vector. So this is what is defined as the scalar triple product. Therefore, whenever we write this kind of expression, it is generally implies that it is basically referring to the same thing. I hope this part is clear to all of you. So this is how we represent or define a scalar triple product. Now, let's try to understand that what is the meaning of this particular thing or scalar trivial product, and what is the geometrical interpretation from it. So if I talk about the geometric interpretation, then let's try to understand what particular thing actually gives us. So again, let us take three vectors, that is A vector, B vector, represent the magnitude of the area of the parallelogram formed by these two vectors. Similarly, if I have these three vectors and let us consider a parallelepiped, okay, a parallelepiped, so whose coterminous edges, so let us try to draw the parallelepiped over here. So let me first draw the 3D axis. So let us say this is x, let us say this is or let us say this is x, Let us say this is y, and let us say this is z, right? Now let us try to draw a vector along y, along x, as this is a vector, this is my b vector, and I try to form a parallelogram based on these two vectors, right? Let us try to draw like this, and also let us take another vector which is out of plane, and let us call this as c vector. So this is my three vectors which form or which have the coterminous edge. So this is basically connected at the same center, or the same terminus point is the same for all these three vectors. So vector system has coterminous. Let us say this is A, and let us say this is D, right? Now we try to complete multiple parallelograms in different planes. So what you notice over here is that we are trying to finish a 3D figure. We are trying to finish a 3D figure by means of these dotted lines. So this particular figure you have is a parallel pipe. So this particular is a 3D figure which we called as parallel pipe. My OB is denoted by B vector and my OC is denoted by C vector. Now, if you recall that when we perform the cross product, so if I just perform the cross product of A cross B, so the cross product of A cross B will give me a vector which is perpendicular to the plane of A and B vector. So this will be something, let us say, so we call that as a eta unit vector, which is the direction of, so unit vector perpendicular to A vector and B vector. So we have a unit vector which is perpendicular to A vector. Now you will try to understand that this has a very important reference that we will try to connect. So when we perform the A cross B vector and then the cosine of the angle between these two vectors. So this particular vector is direction of the angle between these two vectors. So this particular vector is directed along the perpendicular direction, and this makes the C vector makes an angle of phi with the eta unit vector, right, or eta cap. So I have written over here cosine of phi, right? Now if you recall that this magnitude of A cross B vector denotes the area of the parallelogram. So area of the parallelogram OA, B and D. So OABD is the area of this particular parallelogram, so which I am trying to draw by this yellow shaded portion, right? So this I have as the magnitude of A cross B. So this is my area of the parallelogram, and then multiplied, and then what I can represent this particular part as, so this particular part I can write it as multiplied with C vector dot with n cap. This I can write as C vector multiplied with dot with n cap, because I have expressed the A cross B vector as area of the parallelogram multiplied with dot or unit vector along that particular direction, which I can obviously do that because I have seen that any vector can be given as magnitude of the particular vector multiplied with the unit vector, right? So this unit vector actually denotes the direction along which this particular vector is oriented. So I can write like this, and if I take it forward, what I see is that, so I'm writing this part as area of OA BD, and then so AR stands for area, and then this particular product can be written as mod of C into mod of eta cap into cosine of theta. That's what I've written over here, right? Now theta is basically 1, and if I try to understand what is mod of vector C into cosine of phi, sorry, this will be phi, or direction of C vector on eta cap, so which will definitely denote, and then this particular result denotes the height or the height. Now you have learned that in your basics of in your junior classes, in your surface area and volume, you have seen that if I multiply the area with the height of that particular object, volume. So this is what is defined as the volume of the parallel pipe of this 3D figure parallel pipe, which is formed by the coterminous edges A vector, B vector and C vector. So this particular result, that is my scalar dual product, which is the scalar result, So this particular scalar result actually denotes the magnitude of the volume of the parallel pipe whose coterminous edges are given by A vector, B vector and C vector. I hope this is clear to all of you. Is this part clear? Is this part clear to all of you? Please let me know in the live chat. Is this thing clear to all of you? Okay. So whenever we represent the scalar trivial product, it actually refers to the volume of the parallel pipe. Alright. I hope this result is clear. Now, let us try to extrapolate this particular idea to find a relation for coplanar vectors. Now, this scalar trivial product represents the volume of the parallel pipe whose coterminous edges are A vector, B vector and C vector, and obviously they form the right hand system of vectors. So we are going to come into the topic of right hand system of vectors, but for the time being, let's try to understand that if my A, B, C vectors form the right hand system of vectors, then the scalar product of these three vectors denotes the volume of the parallel pipe. Right. Now, if I give you another result from here, if I ask you that what happens when I have A vector, B vector and C vector are three coplanar vectors. So if I ask you that if these three vectors are given as coplanar vectors, if these three vectors are given as coplanar vectors, then what will it happen? Right. So if I have the C vector also to be lying in the same plane, that is of A vector, B vector, then the projection, then when we project this particular result, when we project the C vector onto this n eta cap, I'm going to get this result to be 0. The projection result to be 0, right? So if my three vectors lies in the same plane, then the projection result is going to be 0, and that implies that my scalar trivial product will be simply equals to 0. So whenever this particular relation holds true, this particular relation is a indication that the three vectors are coplanar vectors. So please note this particular result, because we will be using this particular result simultaneously in our solving of questions. I hope this is clear to all of you. Also, let us try to decode one more important implication from this particular result. That is, if I say that my A vector, B vector and C vector box of it or scalar product of it is simply equals to just the multiplication of the magnitudes of the three vectors. When does it holds true? So if it is simply equal to the magnitude of these three vectors, it will hold true when my cosine of phi is equals to 1, and that implies that cosine of phi, that particular phi angle, should be equal to 0. Definitely tell me that this will result holds true when A, B, C vectors are three mutually perpendicular vectors. Are three mutually perpendicular vectors. So whenever I have these three mutually perpendicular vectors, okay, then they will be giving me the result just as follows over here. So please note this particular result as well. So whenever we have three mutually perpendicular vectors, we will just simply have the result of the scalar product as the multiplications of the magnitude of the three individual vectors. I hope this is clear to all of you. Right. Now let us try to also decode the properties that will relate the scalar trivial product. So let's try to understand about the properties of scalar triple product, which I can in short write it as STP. Right. So STP also denotes scalar trivial product. it is different from that what you have studied in chemistry. So chemistry, STP denotes standard temperature and pressure, whereas STP in maths denotes scalar triple product. I hope this part is clear. So let's now go on to understand the importance of scalar triple product. So let us try to understand the first property, and which is a very important property, and you will be seeing these particular properties many times. What is this property talks about? That if I have these three places such that I put this A vector over here and C vector over here and then B vector over here. So what I am doing is that I am doing some even number of interchanges. So what does this particular things refer to? It says that if I take the scalar of, this will be equal to the scalar trivial product of BCA, which is also equal to the scalar trivial product of CCAB. So if I do an even number of interchanges in the position of these vectors, then the result will remain the same. So when I do the even number of cyclic permutation, then the result is remain to be same. So this is also known as cyclic permutation, because when I'm doing cyclic permutation, that basically means that it is an even number. So cyclic permutation refer to even number of changes. Try to solve one important question, that is, let me try to write the question over here. So based on this, let us say the value of scalar trivial product is given to us as 1. This is given in the problem. Then you have to find the value of this particular result, that is you have A dot B cross C divided by C cross A dot B, like this, plus B dot C cross A divided by cross B dot with C, plus try to find out the result of this particular value. So given that you have the scalar trivial product of ABC is given as 1, based on that, please try to evaluate this particular value. Please try to evaluate this particular value. Please try to evaluate this particular value. This is a very simple problem, and let's try to understand how we will solve this problem. So give it a try, then I will discuss about the solution. All right. All right. So let's try to see the solution. So I hope you have given a try, and let's try to see how we can solve this problem. So if I recall from the definitions, plus this can be given as scalar of BCA, box of BCA divided by box product of ABC, and this is also given as box of CAB divided by box of BCA. So if you recall the results that we have discussed in the property, that the cyclic permutation of vectors in order will remain the same. The scalar product value remains the same. So therefore, this particular value is same as this particular value. So this will be cancelled out, and we will have 1. Similarly, this particular result is also same as this particular result, which you can obtain by doing a cyclic permutation over here. So this particular value is also same as this particular value. Again, we will obtain 1, and over here will be the required answer. Alright, so let's try to talk about the second property. So if we talk about the second property talks about that when I do a odd number of interchanges in the scalar dual product result, the result will be just a negative. So that will be, if I do just a single number of interchange or odd number of interchanges, then the result is just a negative of what is the scalar dual product result. Okay, and this is also equal to negative times CBA. So the key results to note over here is that whenever we perform odd number of interchanges, so if I perform odd number of changes, the result is a negative result. And when I do even number of changes, the result remains the same or the positive result. Alright, I hope this is clear. So based on this, let's try to solve again a question. So let's try to see an example. So let us say that I have u vector, v vector and w vector are the three vectors such that I have the result of u vector, v vector, w vector and box product of it, that means the scalar product, is equals to 1. So you have to find out the result of 3 times of u, v, w minus v, w and u, and then minus 2 times of w, v and u. Please try to solve this problem. Alright, if you still have any confusion, any doubts, please let me know. Please let me know if you have any questions, any confusion, so that I can help you out in the live chat. Okay. Alright, so I assume that you have given sufficient time to try this question. So let's try to see the solution. Alright, so if I talk about this particular expression, this can be given as 3 times of box product of u, v, w, which is 1. Now, if we look at this particular expression, it is done by taking a even number of interchanges. So this comes over here, this comes over here, and this goes over here. So this is also similar to that as u box of u, v, w, because it's an even number of interchanges. However, this is obtained by doing a odd number of interchange. So this will be plus 2 times of u, v and w. So if I just evaluate this particular expression, I'm going to get 3 minus 1 plus of 2, which is going to give me the result as equals to 4. So the final result for the expression will be coming out as 4. I hope this is clear to all of you. Right? Is this part clear? Is this part clear to all of you? Just let me know in the live chat. Is this clear? Is this part clear to all of you? Alright, great. Great. So far, so good. Alright, let's now jump into understand the third property. So if we talk about or look into the third property talks about that whenever we interchange the cross and the dot, the result remains the same. What do we mean? In scalar product, the scalar product can be written as A cross B dot C, which is also same as A dot B cross C. A dot B. When I multiply lambda with A vector, mu with B vector, and let us say also we have another constant nu. Alright, so when I multiply nu with C vector, the scalar product result of this is simply equals to the real part or the constant part will come out, and that is lambda mu and nu times A vector, B vector and C vector. Alright, so this is one of the simple implication, and we will see in our questions when we try to solve. Also, scalar product of three vectors are 0 whenever. So we can have scalar product of this result can be 0 whenever we have if two vectors are collinear or parallel. So if any of the two vectors are collinear or if they are parallel, then the result is equal to be 0. Alright, so we will see some questions in our upcoming lectures. Alright, I hope the discussion of the scalar product is clear to all of you. So with this forms the basic idea of scalar product. In our upcoming lecture, we are going to learn about how do we evaluate this scalar product given that we know the components of each of the vectors. So if I give you the vectors in components, then how am I going to evaluate the scalar product? That's what I'm going to do in our next class. So till then, I conclude the session over here and I wish you all the best. So please study these particular properties in detail, and then when we're going to solve question tomorrow, you're going to see that there are some important problems that you can easily solve just by knowing how to find or calculate the evaluation of scalar product. And with that, we're going to soon move into discussing about the ideas of multiple mode properties, and then we're going to discuss about the vector triple product. So that is what is in line in our next lecture. So please try to attend the next lecture, which is going to be another very important lecture on scalar product, because the scalar product results are going to be very useful